Good day, everybody. Today, we'll be talking about chemical bonding. Previously, we learned how to arrange the electrons in the quantum mechanical orbitals. Today, we'll be talking about how the electrons can be transferred or shared between atoms to form chemical bonds. We have learned the valence electrons is the electrons in the outermost shell. For example, in oxygen, the electronic configuration is 1s2, 2s2, and 2s4, and the valence electrons are in 2s2, 2p4, which are the 6 electrons. They are called valence electrons because they are sitting in the outermost shell. To represent the valence electrons, we use so-called a dot structure. For example, the 6 valence electrons for oxygen are represented using 6 dots surrounding the 4 sides of oxygen. Please note the number of valence electrons for any main group element is equal to the group number of the element. Let's see another example. For example, nitrogen is in group 5A. So it has 5 valence electrons. To write the 5 valence electrons, you first write the 1 valence electron on each side. Then, starting from the 5th one, you pair it up. So that's how you write the Lewis structure or dot structure for an atom. Let's see more examples. For example, lithium is in group 1A, so it has 1 valence electrons. You put 1 dot on one side. Beryllium is in group 2A, so that's why it has 2 valence electrons. Boron, carbon, nitrogen, oxygen, fluorine, neon, etc. But do remember helium, although it does have 2 valence electrons, but usually we put these 2 electrons as a pair, as you can see over here. The reason is because helium is forming a stable structure, which is called a duet. For helium, 2 electron outermost electron configuration is very stable. But for the other noble gas structures, you will see 8 electron outermost electronic configuration as the most stable structure. And we call this stable structure or electronic configuration Octet rule. We'll go over more details about the exceptions to Octet rule when we talk about the Lewis structure for covalent compounds. In chemical bonding, electrons are transferred to form the ionic bonds or shared to form covalent bond. Please note, when metal bond with nonmetals, electrons are transferred from the metal to the nonmetal. In the Lewis theory, we can represent this by moving electron dots from metal to the nonmetal. When nonmetal bond with other nonmetals, electrons are shared between atoms rather than transferred. In Lewis theory, we can represent the covalent bonding by allowing neighboring atoms to share some of their valence electrons in order to attain octet, or for hydrogen, it would be duets. So we'll be talking about the Lewis structure for ionic compounds first, then talk about that of the covalent bond. For example, when potassium and chlorine form a compound, the bond that is being formed between potassium and chlorine is the ionic bond, because in the original Lewis dot structure, potassium has 1 electron and Chlorine has 7 valence electrons. So what happened is the 1 valence electron of potassium is being transferred to chlorine. So after that, potassium becomes K+. If you write the electronic configuration of K+, you will notice potassium has 8 electrons in the outermost shell as well. For chlorine, it becomes chloride. It has 1 more valence electron, which means right now it has 8 valence electrons in the outermost shell as well. So both potassium and chlorine now are in the stable electronic configuration. So that's the Lewis structure for potassium chloride. Let's look at another example. In magnesium oxide, okay, magnesium loses 2 valence electrons to oxygen. So we can write it using arrows. 1 electron being lost and another electron being lost. So what happens after losing the 2 electrons, magnesium becomes magnesium ion and oxygen become oxide. In this case, both atoms are becoming ions and have octet being met. One more example. In sodium sulphite, every sulfur gains 2 valence electrons, while each sodium will lose 1. In this case, we write the Lewis structure of sodium sulphite by placing 2 sodium ions on the 2 sides of sulphite. As you might have noticed, the Lewis structure and octet rule for the formation of ionic bond is quite straightforward. Please note, after the transfer of electrons from the metal to non-metal, the cation is without dots. No dot is surrounding the cation, as you can see in the magnesium ion Mg2+. Similarly, in another cation, sodium, there is no more dots surrounding the symbol Na. However, in the anion, for example oxide, you do see 8 dots surrounding it inside a bracket, which is usually used to represent an anion. 2- is indicating the charge. In sulphite, you have 8 dots surrounding sulfur with the bracket. You also have the 2- as the charge. The octet is arrived at by transfer of electrons in the ionic compounds. The octet rule for covalent compounds is more complicated. So let's go over that. Covalent compounds are also so-called molecules. The octet rule for the outer atoms is more straightforward because there are rare exceptions. The only exception is that hydrogen prefers 2 total valence electrons, and all other atoms will prefer 8 total. The octet rule for the center atoms is more complicated because there are many exceptions. For example, beryllium will prefer a total of 4 valence electrons. However, for boron and aluminum, they prefer 6 total valence electrons. But If you give me 8, it's fine. Do remember, all other second row atoms, they can have a maximum of 8 valence electrons. If you give me 9, 10, that's invalid. For all atoms inside the third to the 7th row, they can take 8 valence electrons, but you can give me more. Actually, some of the atoms can even take up to 18 valence electrons. To write the Lewis structures for covalent compounds, we follow a 3-step procedure. First, you want to surround the Lewis symbol for the center atom with those of the outer atoms. So what can serve as the center atom? To remember, hydrogen cannot serve the center atom. And the first element in the formula of the covalent compound is usually the center atom. For example, you have CO2, the first written carbon is the center atom. Okay. You have, in chloroform, CHCl3, carbon, the first written, is the center atom. Okay. Or you have NH3, the first written nitrogen is the center atom. Second step, you want to fill the octet, or in the case for hydrogen, it's a duet for the outer atoms. But how do you connect the outer atoms with the center atom? If the outer atom needs one more, not one, but one more electrons, then you form a single bond. For example, if the outer atom is chlorine, which has 7 valence electrons already, you will need one more to arrive at octet. Then you will form a single bond. For oxygen, which has 6 valence electrons, so it needs 2 more valence electrons, you will need to form a double bond. For nitrogen, which has 5 valence electrons, you will need to form a triple bond with the center atom. So, step 3, check the octet for the center atom. So after step 2, the octet for outer atoms have been met. So we will need to look at the octet for center atom. If the center atom has the right number of valence electrons, what do you mean right number? It doesn't mean it has to have 8. If we review the previous page, as you can see, for example, for beryllium, if you have 4 total valence electrons, that's the right number. And for boron and the aluminum, if you have 6 valence electrons, that's fine. But if you give me 8, that's good too. For all other second row atoms like nitrogen, oxygen, fluorine, if they serve as the center atom, you can take a maximum of 8 valence electrons. And for atoms in the 3rd to 7th row, you can have 8 or more valence electrons. So hopefully you do notice for the center atom there are many exceptions to the octet rule. So let's go back to step 3. So the right number is not necessarily 8. For beryllium, it's 4. For boron and aluminum, 6 is fine, but 8 is also okay, etc. Okay. If the center atom has fewer electrons than needed, then what you need to do is to move the lone pair from the outer atom to form extra bond with the center atom. And if the center atom has more electrons than it can take, then you will need to break a bond and move these electrons inside that bond. Remember, one single bond contains 2 electrons. You break that bond, you move those 2 dots to the outer atom. So let's go over this using the 3 examples as you see over here. So here's the 3 examples. First, CO2. Second, CHCl3. And the last one, NH3. Step 1, you surround the center atom with outer atom Lewis symbols. That's the center atom carbon, And in ammonia NH3, that's the center atom nitrogen. Step 1, you surround the center carbon, which has 4 valence electrons, with outer atoms. Over here, that's 6 valence electrons for each oxygen. So that's step 1. Step 2, you fill the octet for outer atoms. Each oxygen has 6 valence electrons, so it needs 2 more valence electrons, which means you will connect outer atoms using a double bond. Here's how you connect. Starting from the outer atom, you connect the dots. Remember, the dots is becoming part of a newly formed bond. Similarly, for the other oxygen, so that's the second step. So now third step, you do the octet for carbon, which is the center atom. When you look at carbon, carbon has 2 double bonds surrounding it with no more dots left. Each double bond contains 4 electrons inside. So carbon already has 8 electrons. So I'm going to write for this carbon, it has 8 valence electrons surrounding it. So that's good for step 3. So this structure is a good structure, but let's rearrange it so it looks a little bit more beautiful. So for center atom carbon, you have 2 double bonds surrounded by 2 oxygen. Don't forget to copy the dots so that's the Lewis structure for carbon dioxide. For the second example, let's do this stepwise again. Step 1, carbon is the center atom. So we surround the center atom with the outer atoms, hydrogen with 1 valence electron. Each chlorine has 7 valence electrons. You might have noticed that when I write the outer atoms, I try to face their single electron to the center, because then when you connect the outer atom with the center atom, you will not have to curve it around to make a bond. Hydrogen need 1 more valence electrons, so you need to form a single bond. So you connect the hydrogen. With the center atom by connecting the dots. Remember, it's the dots that you're connecting, because the dots are electrons. They are shared to form a bond. So the dots becoming part of the newly formed bond. For each chlorine, they need 1 more valence electron. So each chlorine needs 1 more. The original dots is becoming part of the newly formed bond. Each chlorine needs 1 more. Each chlorine needs 1 more. So notice that the original dots is becoming part of the newly formed bond. So that's step 2. Step 3, remember step 3, you check the octet for center atom. So you look at carbon center. This carbon has 4 single bonds, each containing 2 electrons. So you have a total of 8 electrons surrounding that carbon. So this one does give you 8 valence electrons, because it's a 4 single bonds surrounding that. That means step 3 is done as well. So this structure is already the good structure. So if you want to rewrite it, it's okay, but this one looks pretty good already. Okay, let's work on ammonia NH3. Step 1, write the Lewis symbol for nitrogen, which has 5 valence electrons. Okay, I'm going to surround this nitrogen with hydrogens. Notice I do face these single atom to the center. Each hydrogen has a 1 valence electron, which means it needs 1 more electron. You need 1 more, you form a single bond. So each hydrogen will form a single bond with the center atom. So this hydrogen form a single bond with the center atom. The bottom hydrogen form a single bond with the center atom. The right side hydrogen form a single bond with the center atom. Again, so step 2 is done. Step 3, you check the center atom octet. So nitrogen, when you look at that, nitrogen has how many valence electrons? It has 3 single bonds, that's 6 electrons. And you have 2 dots over there. So 6 plus 2, so that's 8 valence electrons already. So this is good. That means this is the final structure for NH3. So hopefully through these 3 examples you have mastered this method. Okay, let's work on 2 more examples over here. For example, what about SO2? For SO2, sulfur has 6 valence electrons. Oxygen has 6 valence electrons as well. So I put 1 oxygen on the left side, 1 oxygen on the right side. Okay. Each oxygen needs 2 more valence electrons. So you're going to connect using that double bond. But what we are connecting are the dots. So each oxygen is forming a double bond by connecting with connecting the dots. On the right side, it's very similar. So now, when you look at the center atom, sulfur, how many valence electrons does it have? It has 2 double bonds, that's 8 electrons. It also has 2 dots over there. So that's 10 electrons. But you might think, oh, that's more than 8. It's actually okay for sulfur. Sulfur being a 3rd row, this is actually sulfur is in the 3rd row. Okay. So 3rd row you can take 8 or more. So 10 is actually okay. Alright. So if you write this, you can rewrite it so it looks more beautiful. So sulfur has 2 dots and 2 double bonds surrounding it. So copy the oxygen. Alright. But if you want to have sulfur, want to have 8 electrons for sulfur only, then that's also okay. So do remember, that's actually a valid Lewis structure. That's good. Okay. But if you really want to rewrite this so you make sure sulfur has 8 valence electrons, how do you do it? So if we go back to step 3, you do know if you have more than you want to, then you actually you can break a bond. Then you move those 2 electrons to the outer atom, not to the center. Okay. So for sulfur, in this case, so let me rewrite this thing. So that's what you have right now. For sulfur, you have right now 10 valence electrons. As I said, it's okay for sulfur. But if you really want to make sulfur have 8 electrons, you can break this bond. For example, I'm going to break this bond. So you use the arrow to represent the breaking of the bond, and you move those 2 dots to the outer atom. So when you write it, it becomes sulfur. On the left side used to be a double bond, now you break one, so oxygen used to have 6, now those 2 are sitting at the bottom as you see over here. On the right side, it's still a double bond. So that would be another valid structure. So if you break the bond from the right side, you would have a symmetrical one. If you break the bond from right side, okay, as you see over here, rather than the left side, if so, you would see a symmetrical one, as you can see over here. Then the left side will stay as is. The right side will have a single bond. So that's another valid structure, as you can see over here. So all these 3 structures, they are valid, and some are better than the other, but I will not go over this in the intro level. So these structures, the 3 structures you see over here, they are so-called resonance structures. And the difference between them is the placement of electrons, but the connectivity, or how the atoms are connected, are the same. Let's look at one last example. For example, how do you write the Lewis structure for SCl2O? So when you write the Lewis structure for this one, center atom is usually the first written. So you have sulfur here with 6 valence electrons, and chlorine. When you originally write these symbols, you got to do some thinking, right? Because we know chlorine has 7 valence electrons, so we need 1 more. That's why I face this valence electron to the center, to the single electron position, because we know we need to connect these 2 using a single bond. Similarly, for the other chlorine, I'm going to place it over here, because we do know that chlorine has 7 valence electrons. You need to connect it 1 more time. Then I'm going to place oxygen here, because I know each oxygen has 6 valence electrons. You need to connect it with the double bond. On the left side, I need to connect twice because it has 2 dots over here on the center. That's why I want to place my oxygen on the left side. So you do some planning, then your result will look more beautiful. So each chlorine you will connect 1 time. Do remember the original dots is becoming part of the bond. So chlorine is connected to sulfur using a single bond, and for oxygen it's connected twice. The original dots is becoming part of the newly formed bond. So you can rewrite it, but this is pretty good already, okay? Do remember step 3, you need to check the octet for center atom. For sulfur, it has 1 double bond, that's 4 electrons, and 2 single bonds. So each single bond has 2 electrons, so that's also 4 electrons. So you have 8 dots, you have 8 electrons in the bonds, but you also have 2 dots, remember. So you have a total of 10 electrons surrounding it. Remember, for sulfur, sulfur is in the 3rd row in the periodic table. So 3rd row, you can take 8 valence electrons or more. So if you have 10, actually it is okay for sulfur to have 10 valence electrons. By the way, if you have 10 valence electrons for sulfur, we call this expanded octet. Expanded octet, which is more than 8. That's good. So that's the final Lewis structure for SCO2 or SOCO2, right? You can also SOCO2. Okay. That's more commonly written. All right. So that's it for now. We will continue in the next video.